Let's do an experiment to validate the principle of moments. So to start with, here's a scale, and this scale is being balanced at approximately about 50.5 centimeters. That means the center of mass of this scale is exactly at 50.5. And what this also means is the net clockwise moment on this side, because of the mass on this side, the net clockwise moment on this side against this pivot is balanced with the net anti-clockwise moment on the left side. This mass on the left side is trying to pull the scale down on this way, so that's an anti-clockwise torque. And on the right side, what you have is a clockwise torque, right? So that's the point at which we balance. This is called the center of mass. Here you see that scale is balanced exactly at the center of mass. So it is hanging on a thread, and that thread is positioned at approximately 50.5 centimeters. So at this point, the scale is evenly balanced, and we say it's in static equilibrium because it's static and it's balanced, and that's why it's static equilibrium. Now for this experiment, we are going to use these weights, and these weights are approximately about 50 grams. So this one shows it's 52, and we're going to use these small weighing weights, which is approximately 50. So technically we're going to consider both of these as 50 grams essentially. So now in this experiment, what we have done is we have taken the 100 grams on the left, and we have positioned it at approximately 40.5 centimeters. That's about 10 centimeters to the left. And we have a net torque on the left side of about 100 gram force into 10 centimeters. So that's about 1000 gram force centimeters of torque, which is anti-clockwise on the left. Now on the right, this is balanced by a 50 gram force, which is at 70.5 centimeters. And that means that we have positioned the 50 gram force at 20 centimeters from the pivot. So that will be 50 into 20, which is 1000. Again, so 1000 clockwise torque on the right is balanced by 1000 gram force centimeter anti-clockwise torque on the left. So this is a principle of moment. The net anti-clockwise torque is equal to the net clockwise torque, or the other way around. So in this particular case, net anti-clockwise torque is equal to the net clockwise torque for this scale to be in static equilibrium. Now to continue this experiment, let's move this 100 gram force to about 20 centimeters from the pivot. So that's about 50.5 minus 20 would be about 30.5, and that's approximately 30.5. Now if you leave the scale, you see that the scale is not anymore in static equilibrium, because on the left side you have a torque which is equal to 100 into 20. So you see that on the left you have your anti-clockwise torque is 20 into 100 gram force, which is 2000 gram force centimeters on the left, is not balanced with 50 into 20, which is 1000. So on the left you have 2 times more torque than on the right. So this is not in equilibrium. So to make this into equilibrium, we have to provide the same torque on the right side. So to give a 2000 gram force centimeter torque, I have to move this 50 gram force to 40 centimeters mark. So let's move this to about 40 centimeters. To move this to 40 centimeters, you have to move it from the center, which is 50.5. Yep, move that. First make sure that the center is in 50.5. Yeah, move that to 50.5 plus 40, which is 90.5. That's approximately 90.5. It's still not balanced because the center has to be in the 50.5. Yeah, the center should be in 50.5. So the moment we do that, we have now anti-clockwise torque on the left, which is 100 into 20, 2000 gram 4 centimeters, and on the right you have 50 into 40, which is again 2000 gram 4 centimeters. So now you have made this into a static equilibrium. So let's do this activity once more by adding more weight to the left and trying to predict what should happen on the right. Now we have positioned 150 gram force at about 10 centimeters from the center, which is at approximately 40.5, 10 centimeters before 50.5. So the net torque on the left is 150 into 10, which is 1500 gram 4 centimeters. And obviously on the right side you have more torque, which is clockwise torque is more. So we will have to push that 50 gram force to the left so that we can make it into static equilibrium. So by how much? We need to move it such that the net torque on the right should be approximately 1500 gram force, and that happens at 80.5, which is 50.5 plus 30, which is 80.5, 30 into 50, which is about 1500 gram 4 centimeters. So you have the scale again going back into static equilibrium because you have 1500 gram 4 centimeters on the left, which is anti-clockwise torque, balancing with 1500 gram 4 centimeter on the right, which is a clockwise torque. So this is verification of principle of moments.